Hello, Shasta High School Math 1. This is the Chapter 5 Study Team test. This is the test that was given in January of 2016. Let's jump into question number 1. It says, consider the sequence 5, 11, 17. And it asks me to write the next 4 terms in that sequence. If I consider that sequence, there's 2 kinds of sequence that we've been looking at. One of them involves this repeated either repeated addition, and those are arithmetic sequences, and the other one involves repeated multiplication. Those are geometric. This is the case. It's arithmetic. If you look, 11 minus 5 is the number 6. 17 minus 5 is also 6. So as I move forward here, each time I increase the term number by 1, right, the sequence is growing by 6 units. So if I'm asked to write the next 4 terms, that's what it asks for here. After 17, 17 plus 6 is 23. 23 plus 6 would be 29. 29 plus 6 is 35. And then the next one, 35 plus 6 would be 41. So these are the next 4 terms in the sequence. And it does go on. It doesn't stop there, but it just said what are the next 4 terms in it. The generator for this sequence is plus 6 because you can see every single time I move forward, I'm increasing by 6 units. If this was subtraction, if my terms were getting smaller each time by the same amount, my generator would be minus some value, but this is definitely plus. What kind of sequence is it and how can you tell? Well, this is an arithmetic sequence. And the way that I can tell it's arithmetic is it has this hallmark of, it's increasing by using repeated addition. But it could be decreasing as well. In this case, it's increasing by adding the same value. Something like this. It could also be decreasing by adding the same value, right? If the value we were adding was negative each time. But that has to be the case that in an arithmetic sequence, you're either adding, a positive number or you're adding a negative number to continue it. Going to our multiple representations, there's 3 of them here, right? A table, a graph, and a rule in the form of a function. And I guess the sequence itself could be considered the situation, right? So I guess all 4 representations are here. If this column represents our input, I guess I'll put this n inside. If this column represents our input, then this column would represent our output, right? T of n. And our first term was 5. Second, third, fourth, fifth, sixth. Second term was 11. Then we went to 17. And I'm just copying these down. 23, 29, and 35. So the difference, of course, between the sequence and this table, as you can see, I've got both the input, right, what are n's, and then what's the value at that point in the sequence. If I was going to attempt to graph this, I'm going to set this as my origin. I'm going to say every 2 lines is 1. And I don't need to go further than this. And I guess going up, I'm going to count by 5. So each line is 5 units. I'll go 5. I'll call this one 10. This is going to go to 20. This will go to 30. Actually, that's a little small. I could go bigger than that. I'll say I'm going to go every 4 lines is 10. So 1, 2, 3, 4. That's 10. 1, 2, 3, 4. 20. 1, 2, 3, 4. 30. 1, 2, 3, 4. And there's no real right or wrong there. It's just a good idea to kind of use up the space that you have available. So I'm just kind of stretching the scale a bit to make all these things fit. So if I attempt to plot these points, right, at 1, I was at the number 5, which is right between 0 and 10. This would be the 5. At 2, I'm jumping all the way up to 11, which is somewhere approximately here, right? It's in between. At 3, we're going up to 17. That's 10. 2.5 to 15. So the 17 should be pretty close to this point right here. I think on that line would be 17.5. 4 is going to the number 23. So here's 22.5, so about 23, somewhere in here. And 5 is jumping all the way up to 35. That's a nice number, so 30. Oh no, 5 is going to 29. Good, good, good. 5 goes to 29, which is just below here. And then 6 is going to 35, and this will be the last one I plot. That one's a nice one because it's just right where two lines meet. In fact, if I look at it, this first point, right, and this point are really useful for me. Now, because this is an arithmetic sequence, I'm not going to connect these points. Remember, the domain is the set of integers, right? So my domain here, they're actually natural numbers, right? My domain is, I misspoke. Well, actually, no, the domain is the natural numbers. 1, 2, 3, 4, 5, 6, 7. 0 is a whole number. 0 belongs to the set of whole numbers. So I really don't include 0 either because my sequence numbers always start at 1. However, I do need to know the 0th term if I'm going to write the equation for this. The equation of a geometric sequence, right, t of n, that would be, let's see, 6 times n. And then I need to know what the 0th term is. So if you think about this, as I move forward, I'm adding 6 each time. So if I want to go back and figure out what the 0 term is, I'm just going to subtract 6. And 5 minus 6 is at -1. So I've got 6 times n minus 1. And it's nice to kind of plug in your inputs and verify that they do produce the right value. So for example, when I say x is 6, and I plug that value into this function, notice 6 times 6 is 36. And when I subtract 1, I do get 35. So it's at least produced the correct output there. And I'm pretty sure it does it everywhere else. 6 minus 1 is 5 also. So that's our that's our arithmetic sequence. That was the first example there. Just before we move on, I want to make sure that we understand that, this could have very well been a geometric sequence rather. So let's just go ahead and look at one. I wrote down a geometric sequence here. You can see kind of a difference. And if I was to try and do some subtraction, I would see that the number that I'm subtracting each time as I moved forward changed. But if I multiply by 1/3, right? It's the way I prefer to express dividing by 3. If I multiply by 1/3, 81 times 1/3 is 27. 27 times 1/3 is 9. So you can see this sequence involves repeated multiplication of this common ratio of 1/3. In fact, if I was to extend it out, 1/3 or 9 times 1/3 would be 3. And then 3 times 1/3 would give me the number 1. And then I could take 1 times 1/3. I could extend it. That would give me it would give me a 1/3, and the one after that would be 1/9. So what happens now is I just have a new factor of 3 that shows up in the denominator. The next one would be 1/27th. So you can see the difference between an arithmetic sequence rule and a geometric sequence rule. Let's write the arithmetic one from this problem again here. Remember, this was we wrote down that t of n equals 6 times n minus 1. And this one I'm going to say I can't remember if our textbook prefers that we use A's or what for geometric sequence, and it doesn't really matter, but I'll just say I'll call it g of n. It doesn't matter. G of n is, okay, so on a geometric sequence, we do need the 0th term. And moving forward, of course, I'm continuing to multiply by 1/3 to go forward. So if I want to go back and get the 0th term, right, the term that occurred before the 81, and it's not part of the sequence, but the one before that would be 243. So here's my 0th term. So in a geometric sequence, I start with that. I've got 243, and then every single time, if you look, I'm multiplying by 1/3. And I'm going to raise that to the nth power. So here's the beauty of a geometric sequence. And this notation, this number n tells me how many times I multiply by 1/3. So if I want to know, for example, I want to get the third term in this sequence, literally this is what the sequence does. It's doing 243 times 1/3 times 1/3 times 1/3, right? If n is the number 3, because I want not the first, not the second, but I want the third term in the sequence, This notation, right, 243 times 1/3 raised to the nth power, tells me I'm going to multiply by 1/3 3 times. 243 times 1/3 is 81, right? So I'm here. 81 times 1/3 times 81 times 1/3 is 27, and then multiply by one more 1/3 and you're at 9. So this does exactly equal the number 9. So let's summarize this again. So in a geometric sequence, this is the 0 term, right? And this is what I'm multiplying by, my multiplier. In a geometric, and that's a geometric, in an arithmetic sequence, this number right here, and it could be positive or negative, but this is my 0 term. And this is my what I'm adding each time. Right? This is my I want to say my multiplier, my adder. That's what I'm adding each time. And it is the common difference, right? The common difference between each of the terms. And that common difference could be a negative, in which case the arithmetic sequence would be decreasing in size, or it could be positive as it is here, where it's increasing by 6 as we move forward. On this geometric sequence, by the way, if your multiplier is a number greater than 0 but less than 1, the value of that sequence is going to go down over time. And if your multiplier is a number greater than 1, the value of that geometric sequence will increase. So that's pretty much all I need to say about question 1.